Hello everyone, I'm Junseok Kim from George Mason University. On the behalf of our team, I'm going to talk about our approach to the challenge on mobility intervention for epidemics. Due to complexity of human behaviors, predicting the spread of the pandemic is a tremendously the challenge. This uncertainty misguides a policy to mitigate the epidemics and may result in a catastrophic the consequences, such as financial crisis, massive unemployment, and the surge of the number of critical ill patients. The misunderstanding of risks and under or overestimation of the efficacy of intervention can mislead policymakers about the perception of evolving situations. Considering these problems, let me introduce our expert in the loop approach. The goal of our approach is to discover and update the ground truths and evaluate the efficiency and efficacy of each intervention in different situations and reduce combinatorial search space for optimization efficiently. Expert in the loop is a white box approach, and we leverage expert the best knowledge for prescriptive analytics. We repeat the following four steps. The first, we develop heuristics rules to prescribe action to agent. We optimize parameters of these rules to minimize evaluation score and evaluate the pattern within the result by consulting expert to understand resulting patterns and interpret the causality. Then readjust the rules of the following our understanding and intuition. Since it is difficult to control all the factors that may influence outcomes, misconceptions about the public health is common. The cholera was one of them. In 1854, there was outbreak brought straight in the London until the Dr. John Snow traced the source of the cholera epidemic to the specific the water pump. People considered cholera as airborne epidemic. To correct such bias, we utilize modeling and simulation to model the systems. Unlike a black box model, the modeling and simulation provides a deep understanding of the system, and the process of modeling and simulation allows experts to elaborate their knowledge and validate their theory and reasoning. Let me show you one example of the epidemic simulation. This video demonstrates how epidemic spread in our society. Social activities such as eating, the working, and meeting friends derive the social contacts, which are the root of the transmission of the epidemic. You can see the epidemic spread in a spatial network on your left and the social network on your right. Depending on the disease and society, different dynamics of the epidemic emerge. Based on the experience, our goal is to develop micro-simulation that mimics the simulator provided by the workshop challenge organizers. Since the simulated world is different from the real world, we make use of all the documents which are our best knowledge in this world. It includes geographic information, disease model, and so on. Similar to the real world, this knowledge is also our bias, and not all the information is accurate. By experimentation, we could correct our knowledge and discover the ground truths. We develop and calibrate our model to the ground truth model across all these scenarios. The graph on your left is a ground truth model for scenario 1, and on your right is our estimated model. Without the accurate model and parameter, we could not have a decent result in interventions. Before the calibrated model, our score was about 4,000 for scenario 1. After the calibration, our score become 15. Once we have accurate model, we can apply it to other scenarios. By changing the infection rates from the context, we can successfully obtain accurate epidemic curves for scenario 2. One advantage of the modeling simulation is that we can also estimate unobservable data, here the pre-symptomatic. Based on experimentation, we discovered the efficacy of 4 intervention types confinement, quarantine, isolation, and hospitalization. Confinement mitigates somewhat epidemic spreads from the working areas. This option is efficient and effective when the number of infections drastically increases or the number of infections are very large. Initially, we assumed the quarantined individual contact only their acquaintance staying at home. However, by experimentation, we found that diseases from the self-quarantined patients are transmitted to a stranger, which is plausible in the real world. We also discovered its efficacy is similar to confinement, but it's more expensive. For such a reason, we do not use quarantine. Isolated or hospitalized agents are not allowed to contact others, since hospitalization is twice expensive than the isolation. We only consider isolation for the interventions. Based on the discovered ground truths, we come up with the epidemic mitigate strategies. We use two measures to diagnose current state of the susceptible agent. Infection probability is the probability that individual X get infected. It can compute by using contact tracing from discovered cases. A risk factor is a measure of how dangerous X would be if there were the pre-symptomatic. We use general rules with threshold values. If infection probability of X is greater than threshold sigma, then we isolate X. Or if the risk factor is greater than epsilon, then we also isolate X. If the infection probability is greater than the theta, then we confine X. Also, we developed two special treatments, spatial social distancing and temporarily the isolation. Social distancing is a policy to prevent gathering with M or more people. Depending on scenarios, we use a different M. Temporary isolation is a strategy to efficiently isolate a big portion of the population to find many unknown pre-symptomatic patients with much less infections. Let me show you an example. Let the population be 96, and suppose that we have 15 pre-symptomatic cases in orange on day 0. Then infectious agent infect their neighbors with some probability. Next day, we have 10 new pre-symptomatic cases, and the 2 becomes symptomatic. So we isolate 2 symptomatic cases and their neighbors. Now we have 10 isolated agents, and 6 of them are innocent, and we still have 21 infectious agents who are free. Remember that on day 0, we only had 15 infections. If we don't isolate them, the number of infections will increase exponentially. But we have no clue who are the pre-symptomatic. So we randomly but smartly select an agent to temporarily isolate, reduce the new cases. Still, we don't know who are the infectious. However, our selections will guarantee the reduction of the new cases. There are 2 possibilities. First, we isolate pre-symptomatic agent by chance, and they cannot infect others. Second, we isolate susceptible agent that have a high chance to get infected. In this example, we isolate 29 cases, and we luckily isolate 12 infectious agents. Also, about 11 susceptible agents are saved from the infected neighbors. Next day, we discovered 2 new symptomatic cases, and then one of them were already isolated. And the other one couldn't infect anyone because their neighbor were isolated. That we now isolate 12 agents, and we did a temporary isolation once again to suppress the spread. Then we repeat the process. And the next day, we have 2 new symptomatic cases and 2 new pre-symptomatic cases, and overall we successfully isolated 11 out of the 29 cases. In order to discover about 240 unknown cases for scenario, we use these tactics. In conclusion, we introduced the expert in the loop of prescriptive analytics that leverage expert-based knowledge. While the AI and machine learning can outperform in well-defined problems such as optimization, expert can expedite the optimization process. We also demonstrate how the simulation can be used discovered ground truths as a groundwork for prescriptive analysis. We still have a difficulty to narrow down the complex combination rules for scenario 1 and 2 and 4. In order to tackle the combination rules, we will leverage evolutionary algorithms to explore diverse possible worlds for the future work. Thank you for your attention.